learned that there has been a massive attack, a hacker attack, worldwide, 3 terabytes per second, right? Something like that. So apparently, this is happening all over the globe. Okay, just to let you know. Huh? I don't know. Probably not. Hopefully not. Okay, so now we have our last lecture, sadly. Francesco Ginelli, please.
Okay, thank you very much. So we arrived to the end, and I'll give you some kind of introduction to tunnel-into theory. Okay, this may look a little bit like a complicated, exotic subject. Sorry. But I'm trying to make it simple. Of course, in 1 hour and a half, we cannot be exhaustive, but I hope to give you an idea of how things work. Now, the idea of tunnel-into theory in a nutshell is, point 1, use the principle, the phenomenological principle based on symmetry and conservation law, which I introduced yesterday. Okay? Use these to identify the slow field of your theory and to write down all the terms, the evolution equation for these fields, with all the possible terms which do not violate the symmetry and the conservation law of your problem. By the way, as an example, if you have tried to do the exercise that I gave it to you yesterday, you had a set of field equation for the active Ising model. This equation may be derived by symmetry consideration and conservation law. So you had an equation for the time derivative of your density field, and the fact that your density is conserved tells you that it should be possible to write it as the divergence of some flux. Okay? You need this thing here, this derivative in front. Okay, this is already a requirement. These things may be a function of the density, of the magnetization, of their derivatives. And this is basically this requirement conservation or mass. And then you may wonder, okay, you have to wonder, okay, which are the other symmetries we have? The active Ising model is an Ising model, as the name suggests, so you should have a Z2 symmetry. And the Z2 symmetry means that your magnetization, you should be able to switch your magnetization to minus your magnetizations without nothing changing in your equation. But that's not the end of the story. This is the Ising. We are doing the active Ising. What is the active Ising? Is a model in which, if you remember, plus particle like to move to the right, and minus particle like to move to the left. So in this case, you realize that it's not simply that your model should be invariant when you switch from m to minus m. By doing this, you're also making your particle go the other way. So you have also to reflect space. So these should be done in conjunction with spatial derivative going to minus spatial derivatives. Okay? Now, if you impose these two things and you check the equations I gave you yesterday, you will discover these are the most general equation up to second order in the gradients. Okay? That was the way one could derive these equations. Of course, why second order in the gradients? Well, first of all, you have to stop somewhere. Otherwise, you will have an infinite hierarchy of gradients. But the nice thing is that we are interested, I say one last time, in the large scale, long time behavior of our system. And since in Fourier space, a derivative carries a wave number, you realize that in the limit of very small wave number, which means large length scales, higher order derivative became less and less important. Okay? So typically people stops at the second order for a number of reasons, since the second order in the derivatives is diffusion, which is obviously a phenomenon you cannot do without to explain a lot of stuff. And so you should at least go to second order in your gradient expansion. Okay, and this is, of course, small detour. I'm losing my time, but who cares? This is true for systems which are nice, homogeneous. In particular, they don't have sharp boundaries. If you start to introduce sharp boundaries, this becomes a little bit questionable. And indeed, there are indications when you work with boundaries that higher order derivatives may become important, as you expect when you encounter something sharp, okay? But now we are doing a theory which is exact, and the nice thing is that it is exact in these large-scale limits without anything sharp going around. Okay, so two fields, number density, local velocity, all terms allowed by symmetry, gradient expansion. Which is the symmetry, now it's not anymore the Z2 of the active Ising model, is rotational symmetry in space, okay? But rotational symmetry should involve both your velocity and your derivatives, okay? Now your derivatives are gradients, which are vectors, and you want the combination of velocities and gradients to be rotational invariant, okay? So to make a long story short, if you start to think, the minimal set of equations you may write is that one, okay? Which is a little bit awful. Well, here, that's pretty nice. This is just a continuity equation for the density. That's the simplest thing you can write it down. The velocity field is a little bit more complicated. To make things a little bit more manageable for you, if you notice, I use two colors, blue and red. Now, what I'm showing you in blue is essential, okay? Without that, you don't have any of the interesting physics we got. What I'm showing you in red are contributions which are permitted by symmetry. They are there, but they don't change dramatically the physics. They change it a little bit, but since we have 1 hour and a half and not 15 hours, don't focus on that, okay? Anyhow, I'm telling you what these things are. Okay, this is a continuity equation. This time derivative plus this lambda 1 term, notice we have these lambda terms where you have only a single derivative, nabla, nabla, nabla. And you have these d terms, which are diffusion with nabla squared, two derivatives. Okay, so they basically are drift and diffusion as an idea. If you would have normal fluid, this time derivative plus this term with here a factor 1 would be a material derivative. Okay, this is the effect of the advection of the velocity on itself, if you want. And indeed, if you want to have Galilean invariance, that lambda 1 should be 1, and over the lambda 2 and 3 should be 0. Okay? Here we don't have Galilean invariance, since we are moving with respect to a preferred background. So in principle, this is different from 1, and these guys exist, even if we will pretend to ignore them. Then here you have pressure terms, which couples density and velocity field. Here we have diffusion. We always have diffusion. And then we have more anisotropic diffusion terms, anisotropic pressure, and you really don't care about this thing, which complicates your life. Then we have this term here. What is this term? You have seen already with Julia, and you've seen in my exercises. But here there are no derivatives, okay? Alpha minus beta times the square of your velocity, all to multiply the velocity. It can be different. Since it can be different, there is no reason. I mean, the idea is that you need to give me a reason for lambda to be 1. If you don't give me a reason based on symmetries, it can be whatever you like. This is a phenomenological equation. I'm not coarse-graining anything. Just I write all the term I can think of. Okay? So what is this? Sorry? Yes, well, the true active term is this one, which couples. This is not active term. This is something you find in equilibrium. This is the force you can derive by a Landau potential. That things came from this double well potential. Since now V is a vector, is the Mexican hat we were discussing the other day. Okay, that's the potential. This is Vx and Vy. You derive it minus, oops, sorry. No, wrong way. Okay, it's this potential. You derive this and you get a force. Minus this gives you a force. Okay, and this is what breaks the symmetry. This is this is non-active in the sense that you can also break the symmetry in equilibrium XY model, for instance. So this is not where activity comes from. Okay, and here there are, okay, and in the end here there is a noise. This is a Gaussian delta correlated noise, and for this reason this is technically called fluctuating hydrodynamics, since I have this coarse-grained equation and then I put some fluctuation on top, since I would like at a certain point to understand how this system reacts to fluctuations. Okay, it may look intimidating. Okay, the two terms which in blue, but which are underlined are indeed nonlinear terms, which you cannot derive from an equilibrium free energy. Okay, so they are genuinely out of equilibrium terms, are the one who point the trace of activity. Okay, so these are the equations. All the coefficients here you see, so lambdas, 1, 2, 3, sigma, diffusion, alpha, beta, in principle depend themselves on the field, okay? On the density and on the modulo of the velocity. But this is not really important, unless the truly important dependence is alpha, which depends on rho. This has some important physical consequences. The rest is dressing, is not so important. So let's, for simplicity, assume that only alpha depends on the density, and that's the end of the story. Now, you can check with some time that equation are invariant under rotations. Okay, so this is what we need. What we are going to do, okay, there was a discussion which I already did, oops, by hand. I forgot I had it there. Diffusion, viscosity. Okay, but we don't have so much time, so basically we have advection, we have diffusion, we have this Mexican hat, we have a pressure which couples velocity and density, and we have the transport of the density by the velocity. So if you want, your flux, which appear in this equation, is your density times your velocity, which is the most obvious thing you may write. Okay, this is what you have. Now, how do you solve that kind of monster? Well, you solve in the usual way. The first thing you do is you say, okay, first of all, let's pretend we are homogeneous. Here we have a lot of derivatives, but if you look at a stationary solution, which is spatially homogeneous, basically everything disappears but this term here. You see it? Okay? So by doing this, you start to establish that okay, oh, here is a lot of stuff, but that you have a very simple solution, which is if the parameter alpha, you can see immediately, you want this thing to be 0, okay? So if alpha is negative, the only way is the velocity to be 0. What has a state where your coarse-grained velocity is homogeneous at 0 is a disordered state. If alpha is positive, you have a solution which has this modulo, alpha over beta under square root, you see it, which means that you are sitting here on the bottom of this well. This potential has this shape when alpha. Cosa? No, it's alpha over beta, I would say. Here I'm just putting the modulo of my velocity y, since, as I told you, this is spontaneous symmetry breaking. So every solution here in this valley is equally okay. Okay? This is chosen at random. And then we'll see it can fluctuate around. So there is here a phase, if you want, an angle which is irrelevant. All of them are fine. The system selects one, and we are okay with that. So we have this kind of solution, and we establish that it is alpha which is controlling the transition from disorder to order. Then we take this nice solution, which is this one. Okay, we can check the stability and do a lot of stuff. But the first thing you would like to do with this equation is get rid of nonlinearities. Okay? Since you would like to understand how your equation reacts to small perturbation. This is a linear stability analysis. And this is what, if you have done the exercises I gave you yesterday, you should have tried to do with this simple activizing equation. But the idea is exactly the same. Okay? So you linearize your equations. So you go back, sorry. You take these, where is it? You take this solution, which with a constant with 0, which is homogeneous. You, of course, you're homogeneous, you have a constant density, which is the total density of your system, and you put a small perturbation on top of that, both in density and in velocity. Now, velocity, I'm already decomposing the fluctuation along the direction of motion and perpendicular, since I have, let's say, this is my total direction, it's a vector, so I can perturb in this direction, and I call it V perp, or I can perturb longitudinally, and I call it V parallel. So basically, if you want, I have three objects which I'm perturbating: the transversal velocity, the longitudinal velocity, and the density. And with this, I write down linearized equation, which now are all linear. I'm not even writing them down. You can do it by yourself. Linearization is something you can do. But how do you solve a linear equation? Linear partial differential equation? Linear. Linear is a magic word. What do you do? You go to Fourier space. Since in Fourier space, derivatives, which look nasty, became multiplication by the wave number. Okay? Imaginary, square, blah, blah, blah. So you write your spatial structure in Fourier, and you see now your field, your perturbation field, d rho and dv, is a sum of many different Fourier contributions. And since you're linear, all these Fourier contributions decouple. So you look one at a time. And you write an equation which is like this. It's linear. So it's a time derivative of a Fourier mode equal to some matrix for the Fourier modes. Very, very simple, okay? Use this fact that derivatives are multiplication by Q. Okay, to do this, okay, you should do some calculations. So you should take every, okay, linear terms pass transparently to the linearized equation. Non-linear term, you should expand. Here there are a lot of calculations. But there is one interesting thing, okay? focus on this Mexican hat term. Okay, the Mexican hat is this one. I told you we have longitudinal and transversal perturbations. Now you do the expansion. And it means that you're here, this is your homogeneous velocity, now you're expanding. Longitudinally means you're considering this perturbation, which goes against the field. And then you're considering a transversal one, which goes along the valley. Okay? Now, physically, I've already told you what happens. That perturbation along the valley doesn't cost anything. It's flat. Okay? What does it mean? It means that when you expand to linear order, all of this term here, alpha minus beta, b squared, all times v, you see that these things only project along the longitudinal direction. There is no trace of your potential in the transversal direction. Okay? And these things, you have a contribution in the longitudinal direction which does not depend on the derivatives. Okay? So what does this mean according to what we said yesterday? Okay. I need to remind you. Yesterday we discussed about slow mode and fast mode. The slow mode are the one where you only have derivatives. So in Fourier space they are multiplied by q. So when you take the long wavelength limit, their dynamics goes to 0, they are slow. The fast mode are the one which are confined typically by a potential. Okay? So, of course, here in the valley, if you go longitudinally, you expect to be confined. And indeed, this longitudinal term, which is a force, does not depend on the derivative. This is a fast mode. So we can formally eliminate from our equation. Okay? So instead of caring about free fields, which is super boring, it's super difficult, we only need to take care about two fields, and this simplifies the equation. Okay? Of course, this is true everywhere in the ordered phase. It is not true at the threshold, but where at the threshold also this V0 goes to 0, so this thing is small. V0 is the modulo of your velocity. Okay. One thing you should note is that here there is a gamma coefficient. This gamma coefficient is a derivative of this coefficient, this alpha and beta coefficient of the Mexican hat by the density, in particular this one. So this is where this mythological dependence on the density of your alpha linear coefficient comes into play. Okay, it will resurface later. Now, trust me. Remember that there is this contribution. Okay, so you do all of this work. You have this free linearized equation in Fourier space with all the coefficients for the density, the transversal and longitudinal velocity. But the longitudinal, as I told you, is a fast mode. Thank you essentially to this contribution here, which doesn't depend on Q. So what you can do, you can enslave these to the other two fields. And so you get rid of these other two fields. Okay? And at a certain point we will do it, but you see that you have this structure which is linear, and everything, you can make all of this coefficient here into a linearized matrix, which I write here for your convenience. Okay? There are terms in red, since they are the one I choose to ignore in principle. So this makes the analysis simpler. Okay. Now, there are two things you can do with this matrix. You can go and compute the linear stability of this homogeneous solution. We are working in the order regime, so we are ordered. Everyone is flocking in the same direction with a velocity V0. We put a small perturbation on V0 and on the density. So we are here. We have V0. We have R0. this is space. Let's do it in one dimension as a cartoon. And we put a small perturbation, which does like this. Linear stability means to ask, this perturbation, why it's there, since there is a noise, which we are ignoring. So there is noise which constantly put down this kind of perturbation. This perturbation is dying down or is getting increased. This is linear stability. If it dies down, it means that small noise cannot destabilize your system. If it grows, it means that as soon as you arrive and give a little perturbation, everything explodes. And so you will never see this homogeneous order phase. So the game is to understand this, and the language is linear stability analysis. And in Fourier, it amounts to of computing the eigenvalues of this matrix there. Okay? Now, have you followed some introductory course in dynamical system? When you study fixed point, it's basically the same thing. This was a spatio-temporal system, but going into Fourier space, we reduce to ordinary differential equations. These are ordinary differential equations for coupled systems, okay? So, and you know that the stability requirement for a fixed point is that all the eigenvalues should have a real negative part. That is what you want to check, okay? And you can do with this matrix. Okay, you say, oh, it's a 3 by 3, it's annoying. Since 3 by 3 is hard. But you can choose, there are little tricks. Basically, the best thing to do is you choose the directions. You choose a direction. So if your flock is going in this direction, this is with 0, you may start looking wave number in this direction or wave number transverse. Okay? And this simplifies, reduces this problem to 2 by 2. And you're going to discover that if you go here, in this direction, you find the linear instability. You do the analysis. And this is exactly what should happen in the exercises I gave you on the Ising model, which is easier since there you already had to do 2 fields and not 3. Yes? No, it's not only in that direction, but there you can check there is the strongest instability. Okay? And this is a consequence. But especially if you do in that direction, you can do analytically. It's a 2 by 2 matrix, so it's a very easy calculation. You need to do some simplification essentially to expand for wave number, which are small. So you're looking at long wavelengths, which is anyhow where your theory works. You have no control on the short wavelength, so you want to do this. Okay, and if you do this, okay, you end up with this equation for the largest of the 2 eigenvalues, or better, for the one with the largest real part. There is also an imaginary part, but this we don't care. It just gives you spiraling in and out. And as you can see, what happens? This object here is positive, depends on this gamma, and gamma was encoding the density dependence of the linear coefficient. So if you, in principle, have a system where there is no density dependence, the terms will go away, but this is another story. And this positive. So this is an instability, a linear instability. Actually, this term has been obtained also in the limit of small order parameters. So the system is flocking, but it's flocking not to order. So it means that we are close to the threshold to disorder. Okay? And this is exactly coherent with what we see in our Dirac phase diagram numerically. If you remember, we had noise and density. I was drawing like this. And we had this kind of stuff. Here we had gas disorder. Here we have liquid ordered. Okay? And here we have the bands. Now, gas disordered means you are homogeneous, but your V0 is 0. So rho equal rho 0, V0 equals 0. Here, liquid ordered means rho equal rho 0, you are homogeneous in density, and you have a V which is equal to some V0, different from 0. Okay, and that's ordered. This is the state for which we have been looking to the linear stability, and we found that it is linearly unstable at large wavelength. Okay, so it means that here, but it is when you approach this transition line from order to disorder. So here you have an instability, and the instability kills the homogeneous region. Okay, so it should give you structures. Now, this linear theory cannot tell you exactly which kind of structures you're getting, since then it just tells you that perturbation gets amplified. If you want to understand how these structures are, you should do more refined nonlinear analysis. We are not going to enter into this. But the fact that you may find that the stronger instability is longitudinal to the direction of motion, as you asked, means that your instability takes place longitudinally to the direction of motion. So naturally, it leads to bands which are extended transversally. Okay? For instance, I just tell you, if you redo all of this analysis for a nematic theory, dry, not the wet one they were talking about, but if you do a dry nematic theory, you have a different symmetry, you have a very similar structure, but your stability matrix will be a little bit different and will tell you that the strongest instability is transversal to order, not longitudinal. There is the change of symmetry turns the direction of instability. So this is polar. The band you will see nematically will be transversal to the nematic order, for instance. Okay? This is the amount of stuff which you can get out of this theory for linear stability. So in a sense, this Toner-2 theory is able to tell you you're going to have an instability at the threshold by linear stability analysis. Then you can go a little bit deeper, but it's a matter of nonlinear dynamics. So I will give you some reference at the end if you're interested. Okay, this is the summary. Okay, so the summary is this dependence of the Mexican terms on the local density creates the instability at threshold, and it is a long wavelength instability, which, by the way, explains why in the original work by Thomas Witschek it was not seen, since to see a long wavelength instabilities, you need large system size. Otherwise, you don't hit the range of distances of frequency where you see the instability. Okay, any question up to here? This is really a walkthrough, but sorry, if you try to do the exercise I gave you, if you try in the future, you basically understand this mechanism, since it's there in a slightly more simplified setup, and then if you're interested, you can go back here, but at least the physics is really what I'm telling you.
I have a second question.
Yeah.
The unities, entities which form these systems needed to have a capacity to align with each other.
Yes.
But if we have a system with particles, active particles, but without this capacity, which change in the phase diagram?
Different theory. Different theory, different phase diagram. Now, the funny thing is that, as has been discussed during the other lectures, that even if you have scalar particles which are unable to align, for a totally different reason, they also cluster and phase separate. And that's MIPS. Well,
But
actually, the mathematical mechanism, it's also there. It's a linear stability. It's a long wavelength linear instability.
yeah.
But the origin is completely different, and the physics is completely different.
But do you find flocking even when we don't have an explicit alignment term on particles? And we can.
Now, there is a question on what you need to do flocking at the microscopic level. There is, for instance, a paper by an Italian physicist, Caprini, which came out last year, where they claim that they can do flocking in the absence of alignment force, either explicit or implicit. It is, however, wrong. I'm sorry to say it blatantly of another Italian, and it got a comment from a friend of mine, but it is obviously wrong, since it's a case where fluctuation makes you move for a while, but on the long run, there is no flocking.
Sorry, can you explain that again? The spontaneous alignment paper by Caprini and Hartmut-Levin is wrong?
It's wrong, yes. Well, it's wrong in the sense that this is not collective motion. That if you take a very large system, basically, if you take
it's a local flocking.
If you take the value of this thing, which is the common velocity, it goes down, I think, with the square root of a number of particles you put in the system.
Yeah, so it's a local finite size dependent flocking.
Yeah, it's a finite size dependency. So it's not flocking in the rigorous sense.
There is someone here in the room.
Of course, I'm not saying that I'm not saying that it's not interesting.
No, sure.
I mean, all the effects you find in the system are in principle interesting, and there could be some biological system which does exactly that. My only point is that this is not flocking in the theoretical sense and the definition.
Anyway, our colleague here, Nathan Silvano, recently derived a field theory for particles without attraction, and he realized from the field theory that there is this spontaneous flocking. But I don't know if you studied the finite size effect of it. Okay.
Okay, I would like to see the derivation. Now, in general, but if you want, this theory is not a theory which tells you when you're going to have the spontaneous symmetry breaking. It's a theory which tells you if there is the spontaneous symmetry breaking, now I tell you what happens. You may decide if it's useful or not. But you may think that also, I mean, our theory of ferromagnetism is the same. Landau theory is not telling you, I tell you why there is magnetization alignment. I'm just telling you, okay, your system magnetized, then let's have a look at what happens. Okay. Now, the second thing I wanted to tell you is now we more or less try to explain this observation of the phase separation at the threshold. Now let's go deep in the liquid phase, where actually the original paper by John was concerned. John totally missed this instability in the first paper. It was found by other people later. John analyzed this homogeneous phase, assuming that it was stable, which happens if you go deep enough there. And how you analyze? Well, the starting point is against linearization. This is obviously the only thing we know how to do it consistently with a certain easiness. And the strategy will be, first we linearize the equation. We discover from linearized equation we can solve them. We compute the structure factor, 2, one for velocity and one for the density. And we will discover that this structure factor have long-range behavior, long-range correlation, essentially. So they decay as power law. In Fourier space, they diverge, and in real space, you have correlation which decay algebraically. And this is what you can do, basically, with pen and paper calculation very easily, and simple algebra and Fourier transform. Then there is the issue of what you do with the nonlinearities. So far, we are ignoring completely nonlinearity, the elephant in the room. There, the way we know how to treat nonlinearity in this system in a general way, in system which have scale invariance, is the renormalization group. Okay? Out of equilibrium, specifically the dynamical renormalization group, which, of course, I don't have the time to make you deep session, a deep course on renormalization group, but I can give you some ideas of how you use it. And basically, you use it to validate or to correct what you find at the linear level. Okay? We will see that in our case, in physically relevant dimension, we have to correct the linearized finding. Actually, the fact that you need to correct linear behavior goes under the pompous name of breakdown of linearized hydrodynamics, okay? Which tells you the linear results are not exactly true. They get destroyed by the nonlinearity. Okay, so in a very, very quick, I just try to give you the idea. Of course, then you have to do this calculation once in your life, if you really want to see. But again, in the exercise I gave you, there is the same calculation done for the activism model, which is simpler. In that case, I have to say that you will find a different result. Since you're not breaking a continuous symmetry, you will find that your structure factor is not diverging a small q. Okay? So everything is coherent. Here, we have a continuous symmetry. We have this longitudinal free direction, and this creates this algebraic divergence. Okay, but you can really go in the models and have a look. So we have the linearized equation. Now we go in Fourier both in space and in time. So it's all Fourier. And we remember, as I told you, that the longitudinal part was a fast mode. So basically, we can eliminate. You do a little bit of work. I don't have the time to enter into the details, but there is a systematic way to get rid of this fluctuation, which get enslaved to the transversal and the density fluctuation. This is the formula you find to first order in the derivatives. Okay, here we are still in real space. I wrote it in real space. I still have the derivative. Okay, this is the generalization of Reynolds results from the 70s in equilibrium. Okay. So you do it, you put it back in linear space, and okay, finally I did it here. And finally, you Fourier transform space and time. Again, now you have, even better than before, you have only two fields, two coupled equations. These are algebraic equations. You fix wave number. You have these longitudinal and perpendicular wave numbers with respect to the direction of motion. So you're going, your flock is going in this direction. This is Q parallel, and this is, you're looking in the Q perp direction. Easy. And I restated the noise in Fourier space, which is here. We had this noise. So this is linear. I can solve it. How you solve it? This is exactly, the equations are different, but the equation you solve when you do normal, ordinary hydrodynamics, and you try to compute the sound mode. Same thing. So you basically have a stability matrix, 2 by 2, and you can rewrite your equation in this form. You see, phi is a vector which has the perturbation in density and in the velocity, so it's a two-dimensional vector. This is the linear stability matrix we computed before, reduced to the two-dimension, a similar one. And this is your frequency of the Fourier transform in time. So which kind of equation is that? Eigenvalues. I omega are the eigenvalues of M. M is a 2 by 2 matrix. So really, really simple thing, okay? So I omega are the eigenvalues, so the omega are the eigenvalues times a factor minus I. You do the calculation. Calculation is complicated, but it's algebra. You remember always that we stopped, our theory was cut at the second order in the derivatives, which means that nothing which is more than second order in Q, the power of Q square, can be relied in our result, okay? It's all a part we don't control, since it's a short wavelength physics, which we don't know if our Toner-2 equation describes well. So whatever we do, we stop at the second order, and this is the second order. Now, have a look at the form of the second order. You have a dependency, a real dependency on Q, an imaginary dependency on Q square, which multiply these mysterious factors, C plus or minus, K plus or minus, which you don't need to know what they are, but they only depend on the angle theta between the direction of the wave number you're looking at and the direction of motion, okay? But they don't depend on the module of the wave number, okay? When you look at sound waves, the real part of a dispersion relation is the sound speed. Tells you how fast you're propagating, basically. The imaginary part is the dispersion, how fast you get damped. Okay? So the K part, the Q square K part, the imaginary part, is the damping. It's telling you, I have propagating stuff in my system, okay? This is telling you how the signal propagates around. I have two velocities. It's a funny thing, but it is how it is. But you have two, and you have things, propagating waves, which propagate with this velocity QC++ and damped with Q square K++. Now, what happens? The dampings for small q, for only large scales, are much smaller than the velocities, okay? What it means? That if you have long wavelength perturbation, they basically do not get damped, okay? This means that your system can be swept by waves. These are basically spin waves, are made of V-perp, which means are basically birds somewhere are going like this. You move a little bit, you will find birds displaced, bird displaced. Let me make a drawing. These are what in equilibrium physics are known as spin waves. Perturbation like this. Which propagate over very large distances, like very long wavelength waves, okay? They are not damped. These are the Nambu-Goldstone mode of fame, okay? The things also all high energy physicists talk about, but these are these things. That's the mechanism which produces them. Okay, so this proves that here you have all this spontaneous symmetry breaking mechanism, which takes place like in equilibrium systems to a large extent. You can do the calculation. Better, you can first compute the structure factor for the system I gave. Again, there is not a continuous symmetry breaking. So if you do the calculation, you will discover that the imaginary part carries a contribution which is one of the two modes, but this is enough for a reason which you can see later, but carries a contribution which doesn't depend on Q, okay? And that is really the damping. And this tells you that these things get damped. Try to do the calculation, you will see the difference. Okay, this is the awful face of all these coefficient C plus and K plus, which is really awful. There are, okay, but you don't care too much. The point is that once you have found the eigenvalues, apart from discovering that there is propagation, that's a linear system. So you can also compute the propagators. Okay, so the propagators tell you how your system responds to the noise. Now, one technical thing, where is it? Okay, the eigenfrequency, the eigenmodes and the eigenvector, I mean, you find them in the absence of noise. Now you restate the noise, and you want to know it's a kind of response of your system to the noise. And so you just need to solve these two coupled equations. These are linear equations, so you can solve them. Of course, their solution is related to the eigenvalues and the eigenmodes of the eigenproblem. And so it's relatively trivial to compute. It's just boring since you have this very long expression. So we don't have the time to go through the calculation, but you can do it. The point is that you end up with this expression. Okay? These are functions for spatial frequency Q, temporal frequency omega, of the density and velocity in transversal velocity fluctuations, and they depend on the noise. Of course, in the absence of noise, there is no propagator. The propagator is what transfers the noise to the perturbation. So it's propagator times the noise, if you want. Here, this is the omega, this frequency here, and this omega plus and omega minus are these eigenfrequency we found before. Okay. Now you have the single perturbation. They are fluctuating. What is the structure factor? The structure factor is the average over the modulo square of this object, if you want, over delta rho q omega times delta rho minus q minus omega, which is the complex conjugated. And then you take an average. Okay? Since you're taking an average, the only thing which is fluctuating here is the noise, so you're taking average of the noise. When you take the average of the correlation between the noise, two noise at two different frequency, you end up with a delta and with the noise amplitude, large delta, okay? So that's the end of the calculation. These are the correlation function in Fourier space, spatio-temporal correlation function. All linear stuff, admittedly with a lot of algebra, but nothing which probably Mathematica cannot do, with a little bit of patience to write it correctly. Okay, there's this kind of annoying structure, which is rather complicated, but for the moment, we just decide we want to do things simple. We want equal time correlation functions. So to get equal time correlation function, we need to integrate over the temporal frequency. Okay? In principle, to find a correlation function and separated by time t, you should multiply by this Fourier coefficient e to the I omega t. But since we want equal time, t is 0, and this part we get rid of. So we have to carry on this integral. I tried. If you put in Mathematica, Mathematica knows how to do that integral. But you also know how to do it is Cauchy residue theorem, okay? And a little bit of work. That's the result, which again, you say, oh my God, that's horrible. You see, you have this K plus, C minus, C plus. First time you look at it, you read the paper and say, oh my God, what does it mean? But then you realize that all of this depends only on the angle theta between direction of motion where you're looking, but then it's a number, you don't care. All the important thing is here, 1 over q squared, 1 over q squared, okay? That's all you need to know, apart from the rest, which speaks of the anisotropy, but it's so. The density structure factor and the velocity structure factor with different anisotropy factor goes like, okay, the noise amplitude, of course, it has to be there, over q squared. And this is also true. Done. Calculation done. Now, if you remember, this is all I told you was going to happen. I mean, we spent almost 1 hour trying to justify at the linear level the properties I gave you in the previous lecture. Okay? Linear instability of the threshold and the structure factor, which has this power law divergence in 0. Okay, so we're almost there. That's a linearized theory. So we say, bah, okay, I'm satisfied. Let's see what happens, which are the consequences. So this is my scale-free structure factor. There is no anisotropy, since the scaling of all these things doesn't change the large scale anisotropy, so the anisotropy exponent is 1. This implies, here we call this exponent z, so Greek z is 2, and Greek z was a combination of the roughness exponent 2 times, and this d minus 1 plus c, which was the integration over space. There are d minus 1 transversal direction and 1 longitudinal direction. So blah, blah, blah. The roughness exponent as a consequence of 1 and 2 here is 1 minus d half. Done. I have my scaling exponent at the linear level. I can plug them into the thing we already found, giant number fluctuations. Whoa, these are large. Alpha is 2, okay? It's larger than what we've seen in the experiment, and 2 is really strong. It means that the fluctuations, the square fluctuation divided by, the fluctuation divided by the average number of particles doesn't go to 0. You take larger and larger system, and your fluctuations, they grow with the number of particles. So it will tell you this system is not self-averaging, which is bad. And it gives you the idea that this thing is a little bit out of control at the linear level. And indeed, you discover that if you take at face value this result, your theory has no long-range order at the linear level. Okay. How you discover this? Well, you basically want to compute the square fluctuations of the velocity in your system, which is this object here. And this object here, which is the spatial correlation function of the velocity evaluated at zero separation, is given by the integral over the q's of your structure factor, okay? Now, what happens if you integrate, so there is no Lagrange in 2 dimension, of course. What happens if you integrate 1 over q squared in 2 dimension? Does it converge or not? Well, you go in polar coordinate, so this is the q, okay, let's do in d dimension, q in d minus 1 divided by q squared, so it's q in d minus 3. Okay, now on the very small scales, there is a natural cutoff to your theory, which is the lattice spacing. But on large scales, you take an infinite system, what happens to this guy? It diverges if the dimension is less or equal than 2. Okay? The dimension is very large? No. In 3 dimensions, you're safe. It diverges very, very fast in 1 dimension. In 2 dimensions, you see this is 1 over q. So if you integrate 1 over q, you get a logarithm. In d equal 2, you get a logarithm of L, okay? Which diverges logarithmically slow. And this is what it gives you, quasi-long-range order. This is exactly the same result you obtain in equilibrium theory when you analyze the XY model. So take the Nishimori, which is a classical reference. And you will find this calculation. By the way, this is also what happens if you try to analyze seriously by this Fourier space analysis the diffusion equation we wrote for the angle in our hand-waving argument, okay? We wrote this equation, if you remember. if you write this, and you repeat, this was what we wrote down when we said, okay, what happens if you have a series of spins, planar spins on a lattice? They obey this kind of equation. And we did some kind of hand-waving analysis. You can use these techniques on this problem. It's much simpler of Toner and 2. You just have this Laplacian, so it's already linear. You end up with a structure factor which goes like 1 over q squared, okay? And this is what makes rigorous the argument I gave you the other day. So, but at the end of the day, the result is we have a nice linear theory, which, however, does not predict what we see in our microscopic models. Okay? Why? Obviously, since one may suspect that the nonlinearities which so far we blatantly ignored do matter. Okay? And that's the end of the second part, I think. Okay, okay, here there is a note on how you compute the dynamical exponent, but I'm going to skip at the linear level, since I don't want to. Trust me, you get this set of linear level exponents. Z2, by the way, is what you get in diffusion, of course. This is a diffusive kind of phenomenon. Any question? Okay, now, how do you try to build of a linearized theory? Well, the formalism is the formalism of the dynamical renormalization group out of equilibrium, or simply the renormalization group in equilibrium. The idea is essentially simple, okay? The idea is you have a system which is scale invariant, which means, I told you, the correlation length, which is the only scale we had in an infinite system, went to infinity, so we are without any scale. We have power law, which by definition are objects which doesn't change under the rescaling of the scales in your system. So the idea is, okay, let's try to see what happens if we use some kind of magnifying instrument to zoom in and out in my system. So let's start to change the scales which observe my system. And let's see how different scale relates. From this, we can, if the system is scale invariant, we can get a lot of information on how the scale is done. Okay. This operation basically can be done in 2 steps. One requires that you zoom a little bit out and you, in a sense, average over microscopic details. So, who of you have ever saw renormalization in a spin model, which is where typically is introduced? Okay. So, the idea is well, I have a lattice where I have a lot of spins. Let me draw as a little square. Okay, and so on and so forth. The spin, let's think we are doing the icing. It could be 0, plus 1 or minus 1. Let's say yellow is plus 1, and black is minus 1. And I have some configuration, and so on and so forth. And this is a microscopic configuration. Now the idea is, okay, let's zoom a little bit out. Don't focus so much on the details. So let's introduce some larger scale, blocks of 2 by 2, and have some meaningful rule which extract the essential information of which kind of microscopic configuration. Let's say, okay, 2 by 2, it's annoying. Let's do 3 by 3, which is easier. You can also do 2 by 2, but 3 by 3, you have 9 spins in 2 dimensions, which is an odd number. So you may say, okay, if I have more up spin than down spin, I call the big block up. Vice versa, I call it down. And so I basically, this is up, there are more black spins, so this will be all black, and so on and so forth. You see, in a sense, I am integrating over the short scale. This formally means that you need to integrate your equation of motion over all, let's say, the modes which are very large, since very large modes mean very small scales. The interesting thing is that if you do on a linear system, nothing changes, okay? It's the usual fact that if you take anything which is linear, this is transparent to averages or to integration. I mean, you have a linear stuff, you bring in and out without any problem. So when you do visual scaling in a linear system, nothing happens. This is, of course, graining. Then there is a second step, which is, okay, formally rescale my system. And with rescale, you've already seen this. You choose a scaling factor B larger than 1, and you rescale everything, the space, transversal, longitudinal, the fields, the time. But you don't scale with the same factor, since you have anisotropy. You scale according to this famous scaling exponent, which are the one we will use to characterize our theory. Now, the nice thing is that if I do this at the linear level, if there are no nonlinearity, that's all I need to do. Easy. And you say, okay, but we are exactly trying to correct the nonlinearity. Where is the trick? The trick is, now we say, okay, let's suppose, okay, first of all, you can verify that this kind of scaling applied on the linear equation works well. Let me change to the notes. How you enlarge? Like this, okay? Now I'm just really trying to give you a fast... oh, this rotates. Okay, yeah, you can read. Okay, so here I'm trying just take the linearized equation, I apply this exponent, and everything works well. Now, you need to do the nonlinear terms, okay? Now, before going into the details, so let's suppose that you have a single nonlinear term, not many. In the Ising model, it came from the Phi-4 interaction, if you've seen it, and it has. So this kind of, okay. Something I forgot to tell you, that when you do the change of scaling, what you end up is to write the equation which has the same form than before, but where your coefficient has been rescaled, okay? And to have scaling variance, you want that under this rescaling, your coefficient do not change. So you end up with rescaling like the one I wrote here in red, okay? So the diffusion, here there are a lot of constants. The diffusion becomes the old diffusion times b to this power. The noise vertex becomes the old noise amplitude times b to this more complicated power, okay? When they do not change, when everything I have here in this exponent, here b to some powers, when this power is 0, okay? So if you try there the linear scaling exponent we have found, you will find that they make all of these things go to 0, okay? Sometimes you may also have things, in principle, you may think you have some of these exponent, either some of this coefficient, either grow or decay. When this happens, when the exponents here are positive, they grow, they become larger. When they're negative, they became smaller. What does it mean? Well, it means that if they go to 0, it means technically that you brought down something in your equation which disappear under rescaling. It's something irrelevant, which doesn't affect the large-scale physics. You wrote it, but you can forget about that. If you put something instead with the coefficient which grows to infinity under this kind of rescaling, well, it means that it's very important. And you should really take into account that. So the idea is, let's try to do this game also with the nonlinear terms. Let's suppose that they do not count, they are not important. If they are not important, you should not worry of the coarse-graining step, since they don't change the fact that your system is essentially linear. So you say, okay, let's suppose that my system is linear. So I can skip this annoying averaging of nonlinear stuff term, which creates problem. I just do this rescaling step. And then I check if my nonlinear coefficient go to 0, this is consistent with the idea that they don't matter. They are irrelevant, okay? Even if I wrote them, they don't matter at all. On the other hand, if they become larger and larger, it means that they matter. And so I should take into account, and I should restart with them. That's the main idea of how to check if nonlinearity matters or not. Now, you play this game, you have a lot of nonlinearity in this model. Very annoying. Here there is a full list. There are 7 nonlinearity which comes out of your equation, which makes these things very, very complicated. And if you try, you discover that, of course, dimension appears, since, for instance, our roughness exponent key was 1 minus d half. So the result you get depends on the dimension in which you test your things. This is not surprising. If you think of a random walk, you will remember that the fact that your random walk returns to the origin or not depends on the dimension. This is a statement on how strong are the fluctuations in various dimensions. So dimensionality affects the fluctuations. So essentially, it turns out that if you have a very large dimensionality, nonlinearity does not matter. Very large in this case means d larger than 4, okay? Linear is good. But you will discover that if d is less than 4, nonlinear important. Okay. So there is a threshold below which you should take into account nonlinearities, yes?
So the linear stability analysis gives you the sound propagation sectors, or not sectors, but behavior or part information from the linear stability analysis.
Yes.
Is it correct to assume that if I do a dynamic randomization group, I can get the same information in the dynamic randomization group?
I don't know. I don't think you can get that kind of information.
Yeah, I was thinking maybe, I don't know, if I have a critical point and if the critical point is changing the...
No, if you have a critical point, yes, but the point is that the linear instability masks the critical point and create... you know, the result of the linear instability is that there is a critical wavelength, so there is a length scale at the threshold. The fact that you have a length scale tells you you cannot do this scaling analysis.
Okay.
I'm sorry. Yeah. Life is complicated.
I have a question too.
Yes.
What you have there is a kind of a bifurcation, like when you have, for instance, the Wilson-Fisher fixed point and the Gaussian fixed point.
Yeah, it's exactly that. Okay, in the language of grown-up people, this is what happens when you move, you have a bifurcation in the RG flow from the Gaussian fixed point in the phi-4 theory to the Wilson-Fisher fixed point.
Thanks.
Okay, if to you it's pointless jargon, I was trying to keep, but the idea below is this one. All of this has been already been seen in equilibrium system many years ago by very smart people in the 70s, in the 60s. Okay, so the idea is we understood that in d less than 4, nonlinearity are important, okay? Trust me. So it tells you that our linear results can be thrown out of the window. Not all of them, okay? What we learn by these, and okay, I don't have the time to show you, is that yes, our correlation function will still be scale-free, power law, but with different scaling exponent. Okay, that's the entire message of the thing. And okay, here there is a naive power counting idea, which I don't have. Okay.
Just a quick follow-up question.
Yes.
You cannot interpret this d equals 4 as an upper critical
No,
dimension.
this is technically, again, this is the upper critical dimension of the
But then your
theory.
exponent is changing with dimension, for instance.
Yes,
the
yes,
chi.
of course. They are changing with dimension. They do.
Shouldn't it be mean field fixed exponents?
No, 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 no.
Okay.
I mean, here we are going much beyond mean field. So we are, and even the linearized level, your exponent change with dimension, but there is nothing contradictory into that.
Okay.
Okay, so we are near the end. I'm just giving you. So where we arrived? We arrived to the fact that the theory qualitatively holds, we believe, but there are the wrong scaling exponent. So obviously, our structure factors should diverge less violently than 1 over q squared at the nonlinear level in a way to be consistent to our numerical observation in the microscopic models. There are many good arguments for which this should be the case. If you want to do a serious nonlinear analysis by the DRG, now you should also be able to do this averaging step, this integration step, which so far has stayed away from telling you, let's suppose that we are linear, and so that this averaging over the short scale details can be done at no cost. Sad story is that below the upper critical dimension, nonlinearity matters, and you should do this calculation. And this is what it's really hard. This is what people doing RG get trying the lifetime to do this. Okay, these are difficult calculations. Typically, you can only do them in a perturbative way, and the technique used typically is the technique of Feynman diagrams. Okay, all things I cannot do. But what happens if you do this is that the nonlinear correction creates correction which are not to this exponent which we were checking before, but are what is called graphical correction, graphical since they came from Feynman diagrams, and they change this bare value of the constant. So you have this kind of flow equations where not only you have the exponent, but you have d star, d parallel plus a graphical correction you have to compute in a perturbative calculation. And all of these coefficients, and here there are a lot, takes graphical correction. Now you understand that to have all of these things to be scale invariant is not so easy, since you have to compute these, and then you have to find the right combination. This will depend on B, and then you will need to find the right combination of this exponent to make all these things unchanged. It's a mess. This has been done, of course, to a great level of accuracy in equilibrium system. Here, you have a lot of vertex in principle. And it's been computed that even to do a first loop in perturbation theory, you need to compute something like 450 graphs of these, etc. So at a certain point, people got stuck. In the original paper, John and UI too said, but there is at least in two dimension, there are some special symmetries that imply that this graphical correction should be 0. Okay, I'm not going to tell you. They were wrong, and they realized a few years later. So for a while, all our hope of computing exactly the exponent, there was a very good argument for which the divergence of the structure factors should be less than 1 over q squared. So we were sure to have a long-range order, but we couldn't find an exact theoretical value for the scaling exponent. Okay, and so we went to do numerical simulations. Something I have done for a while. And we found a very good number, which is the one I show you for the exponent, analyzing the numerical simulation with a good precision in numerical simulation. If you remember, I also told you that we found at least one hyperscaling relation. Hyperscaling relation means that 3 exponents are related between themselves. And there was a very good numerical evidence that the dynamical exponent z was equal to d minus 1 plus the anisotropy plus 2 times the roughness. And this was an hyperscaling relation, verified in 2 and 3 dimensions numerically. Now, if things happen, they are exactly a sign that there is some symmetry protecting, killing the graphical corrections, okay? And there was a very good indication that this symmetry should have been present in this equation. And, but no one knows how to look for that until very recently. Some time ago, these 2 gentlemen found a very nice idea, okay? And basically, they manage, I don't really have the time to go so much into the details. They manage, well, okay, but I have 5 minutes, and it could be interesting to just convey the idea. Now, there is a point. If you do RG, you learn that all these graphical corrections are way in which let me find, okay, no, Venolina term is in the other. All the graphical corrections happens between terms we have the similar structure. Okay, in particular, you learn that if you have some terms which are exact derivatives and some terms which are not, they cannot interact one with each other. And so you go and look at your equation. These are all the nonlinearities you find. And you discover that this is a total derivative of something. This is a total derivative. 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 Then, these 2, no. If G1 and G2 are different, these 2 objects are not total derivatives. They are correct only if G1 and G2 are the same coefficient. And in principle, there is no reason. So I puzzle myself a lot. I say, okay, but there is a reason for which these 2 guys should be the same. And these 2 gentlemen said, yes, there is a reason. The reason is that you found the wrong Goldstone modes in your theory when you wrote the symmetry-broken theory. Where is it? It's the other thing. So they basically claim that the Goldstone mode has been misidentified in the equation of motion. And that if you write the equation of motion in the symmetry-broken regime correctly, this noise vertex doesn't take any normalization. And indeed, you see, there is no the graphical term, and all you are left is this 3 exponent, these 4 terms, which should be 0, which is exactly this relation. Okay? So they say, why this holds? This is the end of the story. Now you have a lot of other nonlinearities, and they also been so smart to find the 2 other symmetry, which is basically a Galilean invariance of these propagating modes, which protect all the rest. So there are no, I canceled all the graphical correction in this equation. And so you see, you are left with 3 sets of different linear equation for your exponent. You have 3 exponents, 3 independent equations. Bingo. You can compute them. But that is all essentially. Okay? And so you got this result, which in 2 dimensions, their paper treats only 2 spatial dimensions. I asked them, and I also convinced that you can extend probably to 3 dimensions, but still to be done. But in 2 dimensions, you get exact values, which are perfectly consistent with the numerics we have done, okay? So that's essentially the solution. And the explanation of the story is that The true Goldstone mode is not the phase of a velocity for the one who are deep into these things, but it is slightly modified. You should take into account a small correction. If you do this small correction, you obtain the right set of equations. If you don't do, and this is what personally convinced me, this is what Alex showed me. If you remember, I told you this is this nonlinearity, which is not an exact derivative unless G1 and G2 are the same. So he went to simulate the equation numerically already written in the symmetry broken state for different values of G1 minus G2. And unless they are the same, which is this power law line, which is not suppressed, he always finds the suppression, which is the sign in field theory that you introduce in an effective mass, which dampens your Goldstone mode. So for the moment, naive interpretation, some calculation should be needed, is that the misinterpretation of the Goldstone mode caused an effective mass term to appear in the equation, okay? Which prevented further progress. And that's the story which I wanted to tell you. I have to add, to be honest, that to the best of my knowledge, this has been published since a month or something. There is still a debate in the community. In particular, John Toner is objecting over this argument. So don't take everything I tell you as common law in the entire community. There is still a debate going on. I think that this paper is correct, but I'm not I'm not exactly the only and greatest authority in the field. So make your idea. I'm just reporting. But I think that this argument, the counterexample is that you don't write the KPZ equation as a total derivative, but it has to be said in all fair that the KPZ equation is not known to have a Goldstone mode. So it's a different set of systems. Anyhow. But at least the agreement explains the numerical data. Also, there are two other competing papers which find the same result, or three competing papers, I should say. Two rely on some kind of approximation. Another one claims another exact argument for this number to appear, but I don't understand it. So go and read it if you want. I only understood this so far, and the other two have approximations. Okay. I should just give me 3 more minutes, I promise, since there is something I decided to add after a discussion we had, since, okay, I came down from all this theory. Of course, I hope you have at least a map to orient yourself into this complicated thing. But I wanted to go back of the argument of what this theory can tell useful in certain biological conditions. Now, a question I pose myself is, now suppose that you observe a migration phenomenon, cells, for instance, okay? And I spent a lot of time repeating spontaneous symmetry breaking. Spontaneous symmetry breaking means that no one is telling you where you should go. But now you wonder, but maybe someone is telling you where you should go. Maybe cells during embryogenesis are driven, and everyone is convinced, but are driven by chemical gradients. Maybe your animal are not going around choosing the direction at random, but they know where they want to go. They are moving all together, but they have a signal that they are following. So the question is, what this theory is telling you, which lets you distinguish if you have some experimental data, raw data, just let's say the position of your particles, if they are migrating collectively in a spontaneously random direction, or if there is some kind of subtle signal driving them. Okay, that's the question. And this, I think, something which could be useful to biologists, from animal group behavior to cell migration. And the answer is there are two consequences of if you suppose that your system is driven by some spatial inhomogeneity, subtle. There are two ways to realize. One is the most obvious, okay? If you have a finite system with some fluctuation in the directions, it's going to turn sooner or later. And it's going to diffuse away. If you know where to go, you go straight, okay? This is the most obvious thing, but if you have a very small driving, you're going to fluctuate, nevertheless. And you need a long time to observe in which you observe your system to realize that is not turning fast enough. And of course, this time depends on the amount of endogenous noise you have in your system and on the strength of the driving. Okay? Technically, you can show that this amount to the statement that the mean direction of the flocking is an Ornstein-Uhlenbeck process. Okay? And an Ornstein-Uhlenbeck process, which is a random walk taking place in a confining potential, tells you that for a while, at small times, you don't realize that there is a confining potential. And then after a while, your fluctuations don't grow anymore in time and go constant. Okay? And of course, the stronger is the confinement with respect to the noise, the shorter is the time you have to wait. And you have this relation. There is well, other way, sorry. But okay. There you should be a time as a function of the strength of the confinement to the power. Sorry. Should be TC H. H is the strength of the driving to this power 1 over Z, where Z is the renormalized dynamical exponent of the tonality theory. Okay? So it tells you, well, you can wait long enough and you realize. And this tells you how long you should wait. The other way, if you cannot wait a lot, since maybe you have a short time window when you make the observation, you cannot find so much which is the precise direction, but you can count the particle. The other idea is just look at the structure factor, equal time structure factor, which we have seen in all of this lecture that is diverging a small wavelength, but is diverging only if you are spontaneous. If you have a driving anisotropy, then your structure factor is going certain point to bend and go to a constant value. Okay? And of course, the shorter the scale at which happens, the stronger is the driving again. And this is correct. You have this kind of... sorry. This is wrong, of course. I'm tired. That's this correct formula in time. And that is the correct formula in space. It tells you you need a system which is large enough when you play this game to realize that it's driven again. But this way, you have two complementary criteria, which just by looking, you see, you not only need to find sub-chemical traces, you don't need to understand what your animal group is following. You just need to observe the group and either have a look at the temporal fluctuations of the average direction of motion, if you can observe on a very long scale, time scale your system, or at the spatial fluctuations, if you can observe it in a single instant of time, on a short time, but a very large system, okay? So this, it's a practical criterion which in principle can be applied on biological data to distinguish between driven or directed and spontaneous flocking, okay? This is something I would like the biologists to learn how to use it. And this came out of this theory straight. Okay, I think it's more than enough. Sorry for the extra time. Reference of everything I said in these lectures, almost everything. You will find them online. I send it to Pablo, okay?
Thank you very much, Ginelli, for this amazing course. So, questions?
Hi, I have a more general question of a problem that I have for a few months. Can I make a DRG in far-from equilibrium systems? Or do I need scale invariance, argument?
You need scale invariance. As I said, well, as I said beginning of this lecture, the people in Rome has been doing at the treasure of this model, even if there is this long wavelength instability, since their trick is, okay, as long as I am below this wavelength instability, all the scales below are invariant, which is not a formally precise statement. There are a lot of things which may go wrong, but in practice seems to work. This is what I can say. So, or there is people who try to do it if you don't have a formal scale invariance. Sometimes it may work. If you have a little bit of scale invariance, you can learn something. But formally, you need a divergent correlation length to be rigorous.
Yeah. In late March, we're going to have a specialist, an expert in dynamic ORG here, Tomás Grejera.
Ah, okay, yeah, he's one, okay. Yeah. It's, okay, sorry. It's Tomás with the Roman people who's playing this game. Yeah. So he's doing, and he will tell you, yes, you can do it.
He's in your PhD defense committee. Okay, that's great. That's even better, I think.
Say hello to Thomas.
More questions. I have one myself.
Yeah.
Very big picture question. How do you see the future of physics of flocking?
Okay, my personal belief is that, but flocking or active matter?
Flocking.
Okay, flocking. Flocking, I think that we should be able to connect, I mean, to give some kind of meaningful tools or meaningful input to biologists to have a real impact. In general, but you already said, I think that a lot of results and attention came out of active matter in these 30 years, 29 years. But, and there are also, the other lecturers say there are three main interests in active matter. One is to better understand at the fundamental level non-equilibrium physics. And this, I would say, almost checked. I think we learn a lot of stuff more on non-equilibrium statistical physics in these 29 years. There is still more to learn, but we learned a lot of stuff more. We are very happy as physicists, as statistical physicists. We can congratulate between ourselves. And for me, it's more than enough. Okay, I mean, there has been more senior people than me obtaining a lot of this beautiful result, but I think it's really nice. Then it's the question of the larger scale impact of our finding. And I think we are still missing some critical result which matters to biologists, and we are still missing some critical important result which came, for instance, in material science, this hope of devising practical application in active smart material. I don't know if you are more optimistic than me on the possibility to make an impact in this.
Before you and I die, Francesco, we will make a synthetic cell that will do everything that we wanted to do.
But we will make a synthetic cell which is useful, or we will make
synthetic
cells that, oh, nice, we have a synthetic cell.
No. Before we finish making it, people would have come up with 10 uses. Give me 50 years, it's done.
Okay, she's very optimistic. I like her. Sometimes, by nature, I'm more pessimistic. But big disclaimer. Now, you will think that I am a total idiot. But the first time I've been shown a personal computer, I was a little kid in US. I've been shown the first Apple, or one of the first Apple. And they told me, soon there will be one in every house. I say, but come on, it's something for journalists, for why everyone should have one of these things in their house. So I'm not good at predicting future. You should ask someone else. I'm too pessimistic. Okay.
Okay.
Thank you.
So let's think again. Okay, so this is basically the end of the event. Actually, we have coffee break and posters. There is still posters now, so we can still discuss